Welcome back. So we have another problem on application of Newton's second law of motion and drawing of free body diagrams. So the problem reads, a starting gate acts horizontally to restrain a 62 kilogram ski racer on a frictionless 30 degrees slope. So this is a slope. So what horizontal force does the starting gate apply to the skier? Now, the objective of this problem is to ensure that this racer doesn't accelerate. So we'll say the objective, the solution, we want this skier to remain unaccelerated so that's the objective, so that now this, because we have a starting gate acts horizontal to restrain. So that's why we have this term restrain, so that we expect this person not to move from the point where he's attached. So the skier is modeled as an object or objects and we identify the forces acting on the skier, i.e. now this person, there are three forces acting on him. First force is the restraining force due to the gate. Second force is the weight of the skier himself. And then the third force is the normal reaction acting on the skier with respect to this law. So the forces are, i.e. the weight, actually can say force of gravity, another force is the normal reaction, force from the rope, and a horizontal restraining force let's call it F sub H, that we are asked to find. So since we need the acceleration to be 0, that is A to be 0, then the net force is given by MA, implies net force must be 0. And because we have identified that three forces are acting on the object, so if we take this restraining force F plus the normal reaction R plus the weight of the racer, we get their sum should give us 0. Now, so we go back to the diagram and draw an appropriate free body diagram to represent all those three forces of interest. And remember that we have to choose an appropriate axis that can help us to do that resolution of forces. Now, this is how we'll draw the, at this point where we have discussed. So we draw the x-axis. And then we draw this is the y-axis. This is the x-axis. Now, the reason why we are not taking the slope to be our x-axis because we are restraining this racer to be at the point where it's attached to the gate, and then the horizontal force. This is not so the horizontal force will be now force along this x-axis I'm drawing. So this is what we call the horizontal. This is the vertical, and then as we know, because this is a surface, then the normal reaction acts with the normal reaction. It's always perpendicular to the surface. And because this angle is 30 degrees, so then you expect this one also to be theta. This way you'll have the weight. And then if this is theta, then we expect this angle also to be theta. Now, with that, so with that choice of axis, then this is how we'll represent the restraining force. So this will where we have the FH. So this is these are the three forces acting. On this car. So if this angle is 30 degree theta, then you expect this one also to be theta. So now we'll draw a right angle triangle. So you see this is the horizontal axis of the x-axis. So I'll draw another line joining this normal reaction vector to form a right angle triangle that can help me to resolve these forces. And then this line is actually making 90 degrees with the y-axis, and using using Oshachota, then we can tell the length or the magnitude of the forces. This will be this opposite, so this will be simply r, and then sine of theta. This one will be r cosine of theta. And this is the direction. So this is the direction, and this is the direction. So horizontal forces. Now in this diagram, horizontal forces, we have this r sine theta and this restraining force FH. So conventionally, we take forces acting in the right-hand side direction to be positive, forces acting towards the left-hand side to be negative, forces acting upwards to be positive, and forces acting downwards to be negative. So X components X component or the horizontal forces on this diagram so X component, this is horizontal. So Fx should be given by 0 because we expect acceleration to be 0 for this sky. So we'll have this is taken to be positive because it's moving toward the right. So r sine theta. And then this, because the restraining force is acting in the opposite direction to this other force, then it will be negative. Then that should give us 0. Those are the only forces acting in the horizontal direction. That's to mean that the restraining force is given by the normal reaction times sine of theta. And we know theta is 30 degrees. So call this one equation 1. And then y components. So y component, there are only 2 forces. So we have r cos theta, and we have the w, the weight. Weight will be taken to be negative because it's acting downwards, while r cos theta will be taken to be positive because it is acting upwards. So we'll have y component, that's vertical. So we'll have r cos theta minus w should give us 0. So which says w is the same as r cosine of theta. Call this one equation 2. So that's to mean if you make r the subject in equation 2, r will be given by w over cosine of theta. This from equation 2. And so replacing this value of r in equation 1, we get replacing this in equation 1, we have the restraining force is given by, where there's r, you put w over cos theta times sine of theta, which will be the same as sine over cosine is tan. So the restraining force is simply given by the weight times tan of theta. So the restraining force FH will be given by W tan of theta, now which is the same as mg tan theta. Now mass of this racer is 62 kilograms. So we'll have 62 kilograms. G is 9.8 times tan of the angle is 30 degrees. So when you work out this 62 by 9.8 by tan of 30 degrees, you get 350.7980236 newtons. So that is the restraining force on that given sky. So that's how we solve that problem. Thank you.